All right, so today we are going to finish up our section on rational equations. I did post a bunch last night just to kind of give you a heads up on what we were going to do today. The blank questions have already been posted with the notes, so what you're seeing here I posted last evening so that if you wanted to, you could get a quick jump start on getting them into your notebooks. Obviously, if you watch the stream later today or are watching it later today, you will find that you'll be able to pause and move through this a little bit quicker. I do anticipate that we'll be able to get through these couple examples relatively quickly. They're actually pretty easy when it goes down to just have them in your notes and follow the steps. So one of the first things that we're going to look at is work. And you will find that our work problems truly aren't very realistic when it comes down to your typical math word problem. I know there's not a lot of math word problems that are truly realistic, at least at this point. But it's going to be pretty obvious that we're going to be using this strategy with our solving situation. They are very simple rational equations. In fact, we would have never called them rational equations. We would just probably refer to them as fractions, or almost they look like probability. So it is a situation where you're going to most likely see two people or two things trying to get a job done faster. So the first example that I did give for you was mowing the lawn. And it does say that one person can mow the lawn in 40 minutes, but the other person can mow the lawn in 60 minutes. So clearly somebody is much more efficient. It does then say how long would it take them to mow the lawn together. So when we do these work problems, what we're looking at is fractional amounts of time. How much one person can do in a certain amount of time, how much another one person can do in a certain amount of time, and then when that one job needs to get done, how much time would it take total? So when we set up our the work that we want to do, we pretty much the amount of work, the time, we always want to give our time that it takes some kind of variable. So whether it's x, whether it's t, doesn't matter. So we're going to say t is the time to mow. So we want one job that's going to mow the lawn. Now, Peter can do this in 40 minutes. So the one job Peter's going to do, he can do in 40 minutes. And we're going to look at that as 1 over 40. One job in the 40 minutes. And John can do that one job in 60 minutes. And what we're looking at is what would it take for them to do that one job if they worked together. So this idea is John and Peter each hold a fraction of what this job could be done in. You're going to have to be quiet. No, I don't. You can't. Okay? What? Yes, the Wi-Fi just came back on. Sorry. I can't help you with that right now. Anybody still around? Okay, sorry, you just probably heard me yelling at Kara. Thanks, Julie. All right, so we're back up and running. Apparently my Wi-Fi kicked us out. Awesome. So, sorry about that. We're back. Okay. Not sure what happened. I think my Wi-Fi went out. So, all right, so we have this fractional amount, and we're going to add them together, and We're going to set them equal, and now all we have to actually do is solve. And honestly, at this point, I don't care how you solve the fraction. You can do this like we've been doing in this chapter, where you do use the LCM, which, again, we would use our LCM, which would be, in this case, 120. And then you can multiply everything through by that LCM. And in distributing, what you end up finding out is that you end up with 3 plus 2 equals 120 over x. This ends up being a proportion. 5 over 1 equals 120 over x. And when you cross multiply, you end up finding out that x is going to be 24. So in this case, what you're looking at is what should look like a pretty simple equation. When we're adding it together, it's setting it up. And this 24 is the time it takes them together. This is the 24 minutes that we would label. So without all of the extra stuff, let's take a look at Emma, Max, and Carter. Now, curious, are any of Emma, Max, or Carter the 9 of you that might be there? I'm not sure. But again, I did put all of this in last night in case, but it's still going to be this idea of the fractional amount of time that we're going to work. So it does say that they're going to work together to paint this fence. And it says that Emma alone can do the job in 5 hours. Max alone can do it in 6. Together, if they did it, it would take only 2 hours. So what we're looking at is how long would it take Carter to do if Carter had to do it alone. So in this case, we're still going to use that fractional amount of time. We just have to make sure that we break it up into the true fractions. So it says Emma does the job alone, so Emma's one job would take her 5 hours. Max alone would take 6 hours. Carter alone, we don't know, so we're going to make that x, or any variable. But we know that together, it will take them 2 hours. So everything together is always what it's going to be equal to. All of the individual parts are what we're going to have them added up to. So, again, I'm going to get rid of the denominator so that I don't have to worry about fractions. And my 5, 6, x, and 2 have a 30x as our common denominator. And when we distribute 30 to each of these, or I should say 30x, this first one we're left with 6x plus 5x plus 30 will equal 15x. And when we simplify, we're right back to what should be a pretty simple two-step equation. We end up with 30 equals 4x, and x would equal 7.5. And what this tells me is alone Carter takes 7.5 hours to paint the fence. So every time we do a work problem, it is going to be pretty much that simple. Set up your fractions, add them together, set it equal to the total. All right, any questions on that before we switch over to distance? Oh, I've got one more. I apologize. All right, one more work problem. I found this one because it was a little bit different than the other ones. All right, so it says one pipe can fill a pool 1.2 times as fast as a second pipe. Both pipes are opened. They can fill the pool in 5 hours. How long will it take to fill the pool if only the slower pipe was being used? So the only thing we know at this point is that we have two pipes. One is going to be faster than the other. And because we want to talk about fractions, switch before you do anything. 1.25 to a fraction. And that means that we have a pipe that will work 5/4 as fast. So if we went ahead and said X was our slower pipe, then we know 5/4 times X should be faster because it's greater than 1. And it does talk about this job being done in 5 hours. So if we took the two pipes, put them in the pool, it should get done in 5 hours. So we are going to have that one job from the slower pipe. We have our other job from the faster pipe, the 5/4 as fast. And that should finish in that 5 hour period of time. And again, we would choose to solve this however. You could determine this by, again, common denominator, solve your fractions, or stick with what we've been doing in this section, which is what's the common denominator? 20x. And when we distribute 20x, we end up with this first one. The x is going to cancel, so we're left with 20. 4 and x are going to cancel, which leaves us with 5 left over. So 5 times 5 is going to be 25. And then 1/5 of 20 would leave us with 4x. So we end up with 45 equals 4x. So we find out that our x, our slower pipe, would finish it in 11 1/4 hours. Now, if it would have asked how fast both pipes individually would work, we could just change it that way. But again, the whole idea is work breaks this into fractions. All right. Any questions on our work problems? All right, so we're going to switch gears. We're going to talk about distance, and all of this is going to be based off of the formula that we have grown accustomed to, which is distance equals rate times time. So if we're looking at this, please remember D is always distance. R is our rate, miles per hour. and T is always time, hours, minutes, seconds, so on and so forth. And like I made a reference to the other day, this is that situation where it does show up often as a joke, because it can get a little confusing. So the idea is create a table, create a picture if needed. It does make things easier. Word problems were never my strong suit, and I would suggest that even if you had to make sure you understood what was being talked about, especially when if you ever see a problem where it talks about you're swimming upriver and you have to consider, is that going to make you slower or faster, swimming against the stream or with the stream. So again, the adding and subtracting is pretty clear as to what you're going to be working with. So it does say that we're going to take a ship back and forth to Canada, and it took 3 hours less time to get there than it did to get back. The average speed on the trip was 30 kilometers per hour. The average speed back was 20. How many hours did the trip take? So if we set everything up in the idea that we want distance equals rate times time, our trip to Canada talked about our distance. The trip to was 30 kilometers per hour. And it does say the average speed there was, and it says it took 3 hours less time to get there. Well, I need to figure out, how am I going to show time? Do I want to say that to Canada was time minus 3? Do I want to talk about coming back was time plus 3? I will show you in a minute, it doesn't matter. So I want to do this because the first thing it says is it took less time. I'm going to designate this as T minus 3. So when we talk about distance, rate, and time in our table, T minus 3, because that meant it had less time. Back, we have distance equals, and it talks about our speed back was only 20 kilometers per hour. And our time, again, we don't know. This ultimately looks like a system. You have two equations, you have two variables. This acts like a system. We're just solving by substitution. And all we're going to do is set equal to each other. So it is like our systems, and we're going to set these equal to each other in this case. And we end up with 30 times t minus 3 is equal to 20t. So we end up with 30t minus 90 equals 20t. If I subtract the 30, I end up with negative 10. And when I divide, I end up with 9 equals t. So if I plug this back in, to Canada took 6 hours, back took 9. Now, because of course, to make sure that I took care of this and checked to see what would happen if I switched it, just to kind of show you, I did the scratch work before, and I decided if I did, this is how we just did it, but what happens if I decided that distance, my time, when it went faster, meant that it took 3 more hours to get back? So instead of subtracting 3, I added 3 here. Worked out everything using my distributive property, 20 times the t plus 3. And in this case, I got t equals 6. Well, t equals 6, and t plus 3 would equal 9. So if our distance there to Canada was 6, our distance back was 9, it still matches. So it doesn't matter, as long as we address the time difference in our problem. So that's our first distance. Again, we're dealing with everything distance equals rate times time. So let's look at one more. And it says, Ren left school driving towards Cleveland 1 hour before Gus. Gus drove in the opposite direction, going 6 miles per hour slower than Ren. It says they were at the same time 174 miles apart. So that's like saying we stopped them at the exact same moment, and that's where they were apart. What were their speeds? So what we don't know is rate. What we do know is that their distance is affected by rate times time. So if we're looking at what Ren is doing, Ren's distance is her rate times time. So we need to figure out what's the time frame that Ren's been driving. It says that she left 1 hour before Gus, and then later it says 1 hour Gus has also been driving. So what we do know is Ren's time is 2. So we don't know what she's driving at miles per hour, but we do know time is 2 hours. Gus, his distance equals rate times time. It says he's going 6 miles an hour slower. So his rate is going to be -6, whatever Ren's is. But he's only been driving for 1 hour. So we now have distance equals rate times time, just like we did before. The difference here is it wants to know together. They were at the same point that far apart. So we do know distance. Total distance was the 174. So this problem's a little bit different in that it doesn't talk about what their equal distance is. It's talking about their total distance. So when we talk about total, we need to add. So we're going to take Ren's 2R and Gus's 1 times R minus 6 and set that equal to the 174. So we end up with 3R minus 6 equals 174, or 3R equals 180, which we then find out the rate is 60 miles per hour. So 60 miles per hour is Ren speed, which means 54 miles per hour is Gus's speed. So again, looking at what our context clues are, it does tell us how we're going to set this up. We're still working with distance equals rate times time, distance equals rate times time, and then we end up with our total distance, telling us to add them together. The only other thing that we should be reminded about is there is mixture that we talked about last time, loaded that, and wanted to make sure that was addressed. So what you're going to find is that these are the 3 questions that still associate with our chapter section on solving rational equations, so that last section. And if you worked on any of the no-re questions, you did see that that mixture question was addressed at the end. So any questions? Any questions on this? Any questions on anything else that has come up that you would like me to address? All right. I do want to bring up the fact, and you will, if you actually do look through any of the old notes that I'll post, I do want to talk about distance. Our distance formula can be adjusted. We do have this guy that we've grown accustomed to, the distance equals rate times time. But don't forget that if you want to know rate, that's actually R equals D over T. Ooh, I said it and didn't write it. D over T. So sometimes you'll see that it's adjusted that way. And time, if you're actually looking to solve for time, that can get adjusted as T equals distance divided by rate. They all are the same formula. They all do the same thing. It's just a matter of how do you wish to write up your chart. So sometimes you're going to see the problem, and I'll give you an example, and I'll try to keep it so let's just look at Kara is paddling up the Black River. Hopefully there's no bacteria. And in still water, meaning no current whatsoever, her rate is 4 miles per hour. It takes her 2 hours to travel 8 miles round trip. So that means back there and back. And of course, we want to assume that she's going to be traveling at this constant rate. We want to know so again, there's always that disclaimer to make sure that you know that she's not increasing her speed or slowing up. So we have that she's going to be paddling on the Black River, that we do know what her speed is. And it's going to take her 2 hours to travel that 8 miles round trip. She's going to paddle at her constant rate. We want to determine the rate of the current. So now we don't care about her rate. We want to know what's going on with the water. So a couple things we have to decipher here, because we're still using distance, rate, and time. So we know that there's a total distance of 8 miles. So what we could talk about is, with this total distance of 8 miles, because this is round trip, we know that distance is 4 miles in one direction, and distance is 4 miles in the other direction, so traveling there and back. So we do know what distance is. Then what we want to talk about is, if we're going with the current, that means we're going faster. Which means whatever we're going to talk about, we're going to add our speed, because the current's going to make us go faster. If we are going against the current, that's going to slow us down. So that means we're going to end up going slower when we're going against the current. So it does want to talk about the fact that we have time that we're working with. So T equals distance over rate is pretty much the formula that we're going to be using here. Because we know the total time. And that's the total that we're talking about, and that is our 2 hours. So because we're talking about total time, we can adjust our formula if necessary to this. Because we don't know how much time it took in one direction, and we don't know how much time it took in the other direction. We just know the total time. So T equals D over R. So here is our time with the current. So when we're paddling using our current to make us go faster, we went 4 miles, and we ended up with 4 miles per hour, 4 plus R. And then against the current means we're going to have to subtract. And that's going to be our 4 minus R. And our total time is that 2 hours. So because, again, we're talking about total time, we add these together. And here's where you truly get to see this idea of the rational expression. So when we do break this back down, we are going to have the 4 plus R and the 4 minus R as our LCM. So down here, we're going to end up canceling the 4 plus r's. So we're left with 4 times 4 minus r. And then we're going to cancel our 4 minus r's, and we have 4 times 4 plus r. However, over here, there's nothing to cancel, so we end up with what's going to be a quadratic for certain. Now, before we go any further, we are still using our distance formula. The only reason we changed it from d equals rt is this time it told us the total time. The only way we could do this problem is because we don't know how much time it took in each direction. We just knew the total time. So our total time formula, we had to adjust. Which most of us probably have moved on with the problem, but I wanted to make sure that you were aware of why the formula changed and we didn't just use d equals rt every time. So we now have our quadratic. I apparently am writing uphill. And we end up with 16 minus 4r plus 16 plus 4r equals 2 times 16 minus 4r plus 4r minus r squared. These guys we can clearly see are going to cancel. And we are left with 32 equals 2 times, we can see these guys in the middle over here, that was the difference of 2 squares. Those are going to cancel. And we are left with 16 minus r squared. Interesting. I suppose I should have used different numbers. Well, interestingly enough, what we did find, and don't worry, because it does still work, even though what we just found out is that this is 0 equals, I should have made that a 32, negative 2r squared. We end up with 0 equals r squared, so the rate of our current we just found out is still water. So that means there is no current working against or with her. I can honestly say I just changed numbers from another problem that I'll show you here in a second, and it does just show us that the way these numbers are, my 4, my 2, and my 8, it just proved that whatever water in the Black River there is, apparently there is no current at that point. So we would then be able to plug that back in, solve in any other case, and find out how much time eventually. But with what you're looking at with the current, without the current, or against the current, that does work out. We just found out the rate of the current is 0 miles per hour. Now I did do one earlier and just changed it to give you a different example. And I used the same idea where Sandra's rowing, and we have different numbers here. 6 miles per hour in still water. It took her 3 hours round trip. 5 miles in one direction. That's where my 5 kept coming from. 5 miles in the other direction. And in this case, when I crammed it all in, we found the current was 4 miles an hour. So in this case, it does end up working out, and you'll be able to see that quadratic expansion down here. I just wanted to rewrite it so it wasn't crammed in the bottom of the page. And in fact, I ended up cramming it in the bottom of the page and coming out with 0 miles per hour for that situation. So you won't see many like this, but I did want to show you that if it's talking about total time, it would benefit us to adjust our formula. At this point, that does finish the section. As always, you will see all of these examples. I have one that I did with a plane, but didn't want to waste your time doing the quadratic formula via live stream. You can look at that. But yeah, there was a ton that I worked out just to kind of give you an idea that there were variations of this. You won't see that many, at least not until probably pre-calculus, but I did think that it was worth the time to go through it. You will see these uploaded. You will see ones that I worked out previously. You will see a homework problem packet that I used to give that you are not going to be responsible for, but of course I will load them and provide you with the answers to them so that you can kind of see how some of these are worked out. If you want to go further and kind of take a look at them, just take note that when you do the assignment that's required, the notes will come in handy. That way you can kind of go back and forth and view them. I want to be very clear that you do not need to do the distance work and mixture assignment that I'm giving you. It will look like it's on blue and pink paper, but the answers will be provided so you can practice them. I did take time last night to load everything to your Google Classroom. There is an assignment that will be graded. I tried to be as painfully clear as possible, so please make sure, because the only thing we will be doing live on Monday and Wednesday is going over any no-re questions that you have so that that can be finished in a timely fashion so I can start putting that in the grade book, and going over any questions that you have on the required assignment. And I did load that last night. So please make sure that you come prepared Monday. I know I already had somebody last night from the honors geometry class already scanned in and sent pictures to me so that we can discuss them already today. Does anybody have any questions before we end our session for today? All right, if there's no questions, continue to email me your concerns, your questions. We will talk Monday and Wednesday about your questions on the assignment that is required and should be emailed back to me at whatever you decide you're happy with your results. So we will talk Monday. Have a great weekend, everybody. Please stay safe.